You're standing on a planet hurtling through space at 67,000 miles per hour. Right now. This very second. And that planet? It's trapped inside a universe that's expanding faster than the speed of light. Every moment, every heartbeat, the fabric of reality itself stretches into nothing. But here's where your mind shatters. If nothing exists beyond the universe, what exactly is it expanding into? This isn't philosophy. This is the terrifying reality of existence itself. Let me hit you with something that defies everything you think you know about reality. The universe is 93 billion light-years across. That's the observable part. The part we can actually see. But here's the kicker. The universe is only 13.8 billion years old. Wait. Stop. Read that again. How can something that's 13.8 billion years old be 93 billion light-years wide? Light travels at 186,282 miles per second. Nothing moves faster. So in 13.8 billion years, light should only have traveled 13.8 billion light-years. The math doesn't work. Unless space itself is expanding. Not the things in space. Not galaxies flying apart like shrapnel from an explosion. The actual fabric of space-time is stretching, growing, inflating like a balloon. And this expansion? It's accelerating, getting faster. Every single day. Right now, at this very moment, galaxies at the edge of our observable universe are racing away from us at speeds exceeding 299,792 kilometers per second. That's faster than light. Impossible, right? Einstein said nothing can move faster than light. But here's the terrifying loophole. Einstein was right. Nothing can move through space faster than light. But space itself? Space doesn't give a damn about Einstein's speed limit. Space can expand as fast as it wants. And it's expanding into nothing. You feel that? That vertigo? That's your brain trying to comprehend something it wasn't evolved to understand. Your ancestors needed to understand predators and prey, ripe fruit and poisonous plants. They didn't need to understand the expansion of space-time into non-existence. But you do, because you're human. And humans have this beautiful, terrible curse we need to know. So let's break your understanding of reality completely. Imagine you're holding a balloon. Not inflated. Just a sad, deflated piece of rubber. Now draw dots on it with a marker. Each dot represents a galaxy. Draw 100 dots. Cover the entire surface. Now start inflating the balloon. Watch what happens. The dots move apart. Every dot moves away from every other dot. But here's the critical part. No dot is special. If you were standing on any single dot, you'd see all the other dots moving away from you. You'd think you were at the center of the expansion. But you're not. There is no center. Every point in the universe is expanding away from every other point simultaneously. The galaxy you're in right now, the Milky Way, sees every distant galaxy fleeing from it. But an alien in the Andromeda Galaxy? They see the same thing. Every galaxy running away from them. Everyone is at the center. And no one is at the center. Your brain hates this. It wants there to be a center. An origin point. A place where the Big Bang happened. But that place doesn't exist in space. It exists in time. The Big Bang didn't happen somewhere in the universe. It happened everywhere in the universe. All at once. 13.8 billion years ago, every point in space that exists now was compressed into a region smaller than an atom. Infinitely dense. Infinitely hot. And then it exploded into existence. Not into empty space. There was no empty space for it to explode into. Space itself exploded into being. But here's where it gets truly impossible to comprehend. What is space expanding into? Think about that balloon again. As you inflate it, the rubber stretches. The surface area increases. But the balloon is expanding into the air around it. Into the room you're sitting in. Into pre-existing three-dimensional space. But the universe? The universe is everything. By definition, there's nothing outside it. No pre-existing space for it to expand into. No room. No container. No. Outside. So what is it expanding into? The answer shatters every intuition you have about reality. It's not expanding into anything. It's just expanding. Space is creating more space. Distance is increasing. The metric, the actual measurement between points, is getting larger. But there's no outside that it's expanding into. You're probably thinking, that's impossible. That's a word game. That's meaningless. But it's not. Let me give you another way to think about it. Imagine you live on the surface of a sphere. A perfect sphere. And you're a two-dimensional being. You can only perceive and move in 2 dimensions. Forward, backward, left, right. But not up or down. Those dimensions don't exist for you. Now imagine that sphere is expanding. Growing larger. The surface area is increasing. If you're walking in a straight line, and you measure the distance to a landmark, that distance is getting larger over time. The space between you and that landmark is literally increasing. But expanding into what? From your 2-dimensional perspective, it's not expanding into anything. The sphere's surface is all that exists. The 3-dimensional space that the sphere exists in? You can't perceive it. You can't access it. It's not part of your reality. The expansion is intrinsic to the surface itself. The geometry is changing. The curvature is decreasing. But it's not expanding into the 3-dimensional space around it, at least not from your perspective. This is what's happening with our universe. Except our universe is 3-dimensional space expanding through time, and potentially into higher dimensions we can't perceive or access. But here's the part that terrifies cosmologists. We don't actually know if there's anything outside the universe. We can't know. By definition, we can't observe it. We can't measure it. We can't even prove whether the question makes sense. You're trapped inside an expanding reality with no way to see beyond its walls. If there even are walls. Let me hit you with some numbers that will make your head spin. The observable universe, the part we can actually see, has a radius of 46.5 billion light-years. That's 4.4 times 10 to 26 meters. That's 440 septillion meters. In every direction. From Earth, you can see that far. And in all directions, you see basically the same thing. Galaxies. Clusters. Superclusters. The cosmic web. And at the very edge, you see the cosmic microwave background, the afterglow of the Big Bang itself, light that's been traveling toward you for 13.8 billion years. But here's the impossible part. That light started its journey when the universe was much smaller. When the light was emitted, the object that emitted it was only 42 million light-years away from where Earth would eventually form. Today, that same object is 46.5 billion light-years away. The light took 13.8 billion years to reach us. But in that time, space expanded. The source of the light got dragged away by the expansion of space faster than the light could travel. That's not science fiction. That's measured, observed, confirmed. Every second, space is creating more space. Between you and the most distant galaxies we can see, 20,000 kilometers of new space comes into existence every single second. 20,000 kilometers. Every second. That's like inserting half the circumference of Earth between you and those distant galaxies every single second. And it's accelerating. Something called dark energy is pushing space apart faster and faster. We don't know what dark energy is. We can't see it. We can't touch it. We can barely even detect it. But it makes up 68% of the universe. 68% of everything that exists is this mysterious force that's tearing space apart. And here's the truly terrifying part. If this continues, and all evidence suggests it will, the universe will end in what cosmologists call the Big Rip. Billions of years from now, the expansion will accelerate so much that galaxies will be torn apart. Then solar systems. Then planets. Then molecules. Then atoms. Then subatomic particles themselves will be ripped apart by the expansion of space-time. Everything will be separated from everything else by such vast distances that no force, no particle, No information can bridge the gap. The universe will be nothing but isolated photons, drifting alone in an infinite, expanding void, unable to interact with anything, ever again. Entropy wins. Coldness wins. Separation wins. But that's billions of years away. Right now, you're worried about something more immediate. What the hell does it mean for space to expand without expanding into something? Let me try to break your brain in a different way. Think about numbers. Positive integers. 1, 2, 3, 4, and so on, stretching to infinity. Now imagine we somehow expand the space between numbers. We insert more numbers. Between 1 and 2, we insert 1.5. Between 1 and 1.5, we insert 1.25. We keep adding more and more numbers in between. The set of numbers grows. It becomes more dense. More infinite, if that makes sense. But it's not expanding into anything. The number line doesn't exist in physical space. It's an abstract mathematical object. Its expansion is intrinsic to itself. This is closer to what's happening with the universe. The expansion isn't happening in some pre-existing framework. The expansion is the framework changing. Reality itself is stretching. The geometry of space-time is dynamic. It's not a fixed stage where events play out. It's an active participant. A living, breathing, expanding entity. And you're inside it. You're made of it. Every atom in your body exists within this expanding space-time. You are a temporary pattern of matter and energy, surfing on the fabric of reality itself as it stretches into nothing. But here's something even more mind-bending. The universe might be infinite. Wait. What? If the universe is infinite, then it was always infinite. Even at the moment of the Big Bang, it was infinite. Just infinitely dense. An infinite universe can still expand. Every finite region within it can grow larger. The distance between any 2 points can increase. But the universe itself? Still infinite. You can't make infinity bigger. But you can make every finite piece of it larger. Imagine an infinite line marked with integers -3, -2, -1, 0, 1, 2, 3. Now stretch it so that the integers are twice as far apart. The line is still infinite. But the spacing has changed. That's cosmic expansion in an infinite universe. So if the universe is infinite, the question, what is it expanding into, becomes even more meaningless. An infinite universe isn't expanding into anything. It's just stretching. But we don't know if the universe is infinite. We might never know. The observable universe is finite. We can only see so far. Light from more distant regions hasn't had time to reach us yet. And because of cosmic expansion, light from sufficiently distant regions never will reach us. There's a cosmic horizon. Beyond it, we cannot see, cannot know, cannot measure. For all we know, our observable universe, that 93 billion light-year sphere, is just a tiny bubble in an infinite cosmic ocean. Or it might be all there is. We don't know. And here's the terrifying part, we might never know. But it gets worse. Remember how I said the expansion is accelerating? That acceleration means that galaxies currently within our observable universe will eventually expand beyond our cosmic horizon. In trillions of years, the Milky Way will be alone. Every other galaxy will have been carried away by cosmic expansion, receding faster than light, vanishing beyond the horizon of what's observable. Future civilizations, if any exist, will look out into space and see nothing. Just their own galaxy, surrounded by infinite darkness. They'll have no evidence that other galaxies ever existed. No evidence of the Big Bang. No cosmic microwave background. No expanding universe. They'll think they live in a small, static, eternal universe consisting of one galaxy surrounded by emptiness. They'll be wrong. But they'll have no way to know they're wrong. All the evidence will have literally moved beyond their reach. We live in a special time. A brief window in cosmic history when we can actually observe the universe's expansion. When we can see the afterglow of the Big Bang. When we can peer billions of light years into space and time. But that window is closing. Every second, more of the universe slips beyond our horizon. Forever. You might be thinking, okay, but that's just our perspective. The universe is still there, beyond our horizon, even if we can't see it. True. But here's the question that should keep you awake at night. Is there a difference between something that exists but can never be observed, measured, or interacted with, and something that doesn't exist at all? If a region of space can never affect you, can never send you light or information, can never be visited even in principle, does it meaningfully exist in your universe? This is where physics bleeds into philosophy, and where your intuitions about reality completely break down. Let's go deeper into the geometry of this impossible situation. When cosmologists talk about the expansion of the universe, they're talking about something called the scale factor. Think of it as a number that describes how stretched space is at any given time. As time moves forward, the scale factor increases. Space stretches. But here's the crucial detail. This stretching isn't the same everywhere. On small scales, like inside your body, inside the solar system, even inside our galaxy, gravity is strong enough to hold things together. Space isn't expanding between the atoms in your body. It's not expanding between Earth and the Sun. It's not even expanding between the stars in the Milky Way. Gravity resists the expansion. On these scales, gravity wins. It's only on the largest scales, between galaxies, between galaxy clusters, between superclusters, that expansion dominates. Where gravity is weak, where the dark energy pushing space apart overwhelms the gravitational attraction pulling things together. So you're not expanding. Your atoms aren't getting farther apart. The solar system isn't growing. Even the Milky Way maintains its size. But the space between the Milky Way and the Andromeda Galaxy? That's growing. Well, actually, no. Andromeda is moving toward us. It's going to collide with the Milky Way in about 4.5 billion years. The two galaxies will merge into one enormous elliptical galaxy that astronomers have already nicknamed Milkomeda. Why is Andromeda approaching if space is expanding? Because Andromeda is close enough that its gravitational attraction to the Milky Way overwhelms the expansion of space between them. But galaxies farther away? Those are being carried off by expansion. And the farther away they are, the faster they're receding. This relationship was discovered by Edwin Hubble in 1929. He found that the recession velocity of distant galaxies is proportional to their distance. Double the distance, double the recession speed. This proportionality constant is called the Hubble constant. Currently, it's about 70 kilometers per second per megaparsec. What does that mean? It means for every megaparsec of distance, that's 3.26 million light years, the recession velocity increases by 70 kilometers per second. A galaxy 10 megaparsecs away recedes at 700 kilometers per second. A galaxy 100 megaparsecs away recedes at 7,000 kilometers per second. A galaxy 1,000 megaparsecs away recedes at 70,000 kilometers per second. Do the math far enough, and you quickly reach distances where the recession velocity exceeds the speed of light. And we've observed galaxies whose recession velocity is over 3 times the speed of light. 3 times. 300% of the cosmic speed limit. How is that possible? Because they're not moving through space faster than light. The space between us and them is expanding, creating more distance, more space, faster than light can cross it. Imagine you're an ant on a rubber band. The rubber band is 1 meter long. You can walk at 1 centimeter per second. If the rubber band isn't stretching, you can walk from one end to the other in 100 seconds. But now imagine the rubber band is stretching. Every second, it gets 10 centimeters longer. You're still walking at 1 centimeter per second. But every step you take, the destination gets farther away. Can you ever reach the other end? Depends on where you start. If you start close enough, yes. Your walking speed can overcome the stretching. But if you start too far away, the stretching outpaces your walking. You'll walk forever, making progress in your own frame of reference, but never actually reaching the destination because it's receding faster than you can approach. This is what's happening to light in our expanding universe. Light from sufficiently distant galaxies is traveling toward us at the speed of light. But the space between us is expanding faster than that. The light makes progress, it's not standing still, but the destination keeps receding. Some of that light will eventually reach us. In billions or trillions of years it'll arrive. But light from galaxies beyond a certain distance, beyond what's called the cosmic event horizon, will never reach us. Ever. The expansion is too fast. The distance too great. Those galaxies are still there. They still exist. They're still emitting light. But that light will never, ever reach us. We are cosmically isolated from them. Forever. And they're isolated from us. If there are beings on a planet orbiting a star in one of those ultra-distant galaxies, they can never know we exist. And we can never know they exist. No information can ever pass between us. For all practical purposes, we exist in separate, causally disconnected regions of space-time. Separate universes, in a sense. This is what physicists call cosmic horizons. Not horizons in space, but horizons in space-time. Boundaries beyond which cause and effect cannot operate. Where information cannot flow. And those horizons are shrinking. Every second, more of the universe slips beyond our reach. But let's get back to the original question: what is the universe expanding into? Here's where general relativity, Einstein's theory of gravity and space-time, gives us the answer. Or rather, tells us why the question doesn't make sense. In general relativity, space-time isn't a thing in the universe. It is the universe. Matter and energy tell space-time how to curve. Space-time tells matter and energy how to move. They're inseparable. Two aspects of the same reality. When we say the universe is expanding, we mean the metric of space-time is changing. The distances between points are increasing. But this increase is intrinsic to the geometry itself. It's not an expansion into some pre-existing background. Think about temperature. When something gets hotter, the temperature increases. But the temperature isn't moving into anything. It's not expanding into some temperature space. The property itself is changing. That's what's happening with space. The property of distance is changing. The metric is evolving. But there's no external framework this is happening in. Or at least, none that we can observe or that affects us in any measurable way. But, and this is a big but, we can imagine scenarios where the question does make sense. Some theories suggest our universe might be a four-dimensional surface of a five-dimensional object. Like that two-dimensional sphere I mentioned earlier. The sphere's surface is two-dimensional, but it's embedded in three-dimensional space. Maybe our three-dimensional universe is embedded in a higher-dimensional space. In these theories, called brane cosmology, our universe is a brane, a three-dimensional membrane, floating in a higher-dimensional bulk. In such a scenario, the universe could be expanding into that higher-dimensional bulk. The brane could be growing, stretching, moving through the bulk. But here's the catch: we can't access that bulk. We can't see it. We can't measure it. We're confined to the brane. All the forces we know, electromagnetism, the strong and weak nuclear forces, are confined to the brane. Only gravity might leak into the bulk. Which is why gravity is so much weaker than the other forces. It's diluted across higher dimensions. This is speculation. Brilliant, mathematically sophisticated speculation. But speculation nonetheless. We have no direct evidence for extra dimensions. No observations that require them. They're possible. Consistent with physics. But not proven. So the honest answer remains: we don't know what the universe is expanding into. And it's not clear the question is meaningful. But here's what we do know: space is expanding. The distances between distant galaxies are increasing. This expansion is accelerating. And if current trends continue, the universe will eventually become cold, dark, empty, and unimaginably vast. Every structure we see today, galaxies, stars, planets, even atoms, will be torn apart by the relentless expansion. And in the end, all that will remain are isolated particles, separated by distances so vast that they might as well be alone in their own private universes. This is the heat death. The Big Freeze. The ultimate fate of a universe dominated by dark energy. Unless something changes. Unless dark energy itself evolves. Unless the laws of physics have surprises we haven't discovered yet. Which brings me to something even more mind-bending. The universe might not be expanding into nothing. It might be expanding into other universes. Stay with me. One of the leading theories in cosmology is called eternal inflation. The idea is that the Big Bang, the moment when our universe began, wasn't a unique, one-time event. It was one bubble in an infinite, eternal process of bubble making. Here's how it works. In the earliest moments after the Big Bang, the universe underwent a period of incredibly rapid expansion called inflation. In a tiny fraction of a second, about 10 to 32 seconds, the universe expanded by a factor of at least 10 to 26. That's more than doubling in size 86 times in less than a trillionth of a trillionth of a trillionth of a second. This inflation was driven by a field called the inflaton field. When this field was in a high-energy state, it caused space to expand exponentially. When the field transitioned to a low-energy state, inflation ended, and the energy of the inflaton field was converted into matter and radiation. The hot, dense soup that became our universe. But here's the kicker, inflation might not have ended everywhere at once. The inflaton field might still be in its high-energy state in some regions. Those regions would still be inflating, expanding exponentially, ballooning into vast, empty voids. But occasionally, randomly, the inflaton field in a small region would transition to its low-energy state. That region would stop inflating. It would heat up. Particles would form. A new universe would be born. Our universe might be one such region. A bubble that stopped inflating 13.8 billion years ago. But outside our bubble, inflation continues. Eternal. Infinite. Always creating new bubbles. New universes. Each bubble is causally disconnected from the others. Light can't travel between them. Information can't pass between them. Each bubble is its own universe, with its own laws of physics, its own constants, its own history. And there are infinitely many of them. Forever being born. Forever inflating. Forever creating more bubbles. This is the multiverse. And if it's real, then our universe is expanding into a larger structure. A vast, inflating megaspace dotted with bubble universes like ours. But we can never observe those other bubbles. We're trapped inside ours. The expansion of our bubble's boundary is faster than light. We can never reach it. Never see beyond it. Never confirm whether other bubbles exist. Again, we're faced with the question, does something that can never be observed meaningfully exist? And again, physics offers no clear answer. Only possibilities. Speculations. Mathematical consistency. Let me hit you with another angle on this impossible question. Think about what it means for space to be nothing. We talk about empty space. Vacuum. Void. But is space really nothing? Not according to quantum mechanics. Quantum mechanics tells us that empty space isn't empty. It's seething with activity. Virtual particles constantly pop into existence, exist for a tiny fraction of a second, then annihilate each other and vanish. This isn't speculation. We've measured it. The Casimir effect. Hawking radiation. Lamb shift. All consequences of the quantum fluctuations of empty space. Empty space has energy, called vacuum energy or zero-point energy. And that energy might be what's driving the accelerated expansion of the universe. Dark energy might literally be the energy of empty space itself. Which means as space expands, creating more volume, it's creating more vacuum energy. Which creates more expansion. Which creates more space. Which creates more energy. A runaway feedback loop, leading to the Big Rip. But here's the thing, if empty space has energy, and that energy is intrinsic to space itself, then space isn't nothing. It's something. A quantum field. A dynamic, fluctuating entity with physical properties. So when the universe expands, it's not expanding into nothing. It's expanding into more of itself. More quantum fields. More vacuum. more something that looks like nothing but isn't. This might sound like word games, but it's not. It's a deep insight into the nature of reality. Nothingness, true, absolute nothingness, might not exist, might not be possible. Everywhere space exists, quantum fields exist. And where quantum fields exist, things happen. Virtual particles fluctuate. Energy percolates. So the universe expands into more universe, more quantum fields, more vacuum, more potential for something to happen. Not nothing. Never nothing. Because nothing isn't stable. Nothing decays into something. Quantum mechanics demands it. This is the insight that led Lawrence Krauss to write a book called A Universe from Nothing. His argument, given quantum mechanics and general relativity, a universe can spontaneously emerge from nothing. Or rather, from the quantum fluctuations of the vacuum, which might be the closest thing to nothing that exists. But even that's not truly nothing. It's still a quantum state. Still something governed by laws. Still something rather than absolute, philosophical nothing. Maybe absolute nothing is impossible. Maybe the default state of reality is something. Fluctuating quantum fields. Expanding space-time. Eternal inflation. Universes bubbling into existence like foam on an infinite ocean. And maybe the question, what existed before the Big Bang? Or, what is the universe expanding into? Is like asking, what's north of the North Pole? It's a grammatically correct question, but it doesn't have an answer, because it's based on a false assumption. The assumption that time extends infinitely into the past. That space requires a container to expand into. Time began at the Big Bang. Or at least, our timeline did. Asking what came before is like asking what's north of the North Pole. The question doesn't make sense. Not because we don't know the answer. Because there isn't an answer. The question itself is malformed. Similarly, space doesn't require a container. It is the container. It contains itself. And as it expands, it creates more container, more space, more room for stuff to exist. This is the universe. Self-contained, self-creating, expanding into itself. But let's not pretend this is satisfying. It's not. Your brain still wants to know, but what is it expanding into? And the answer, nothing, or itself, or the question doesn't make sense. Feels like a dodge. Like physicists giving up. Like they're hiding behind mathematics and semantics rather than giving you a real answer. But they're not. They're being honest. They're telling you that your intuitions, built from living in a world of objects and containers, of things moving through pre-existing space, don't apply to the universe as a whole. The universe plays by different rules. Rules that math can describe but words struggle with. Rules that defy visualization. You can't picture the expansion of space. You can't imagine nothingness. You can't visualize higher dimensions or infinite sets or space-time curvature. But you can describe them mathematically. You can calculate with them. Make predictions. Test those predictions. And the predictions match reality. General relativity predicts the expansion of the universe. Predicted it before we observed it. Predicted the Big Bang. Predicted black holes. Predicted gravitational waves. All confirmed by observation. Quantum mechanics predicts vacuum energy. Virtual particles. Quantum fluctuations. All confirmed. The math works. The predictions come true. The theories are correct, even if they're impossible to visualize. So when physicists say the universe expands without expanding into anything, they're not being evasive. They're telling you what the math says, what the observations show, what reality is, as far as we can measure, even if it makes no intuitive sense. And maybe that's the deepest lesson here. Reality doesn't care about your intuitions. Doesn't care if you can visualize it. Doesn't care if it makes sense to a brain evolved to hunt gazelles on the African savanna. Reality is what it is. And what it is, apparently, is much stranger than your ancestors ever needed to imagine. But here's something even more unsettling. Something that keeps cosmologists awake at night. We don't know if the universe will expand forever. Right now, all evidence suggests it will. Dark energy is pushing space apart. That expansion is accelerating. If nothing changes, the universe will expand forever, cooling and darkening until it reaches heat death. But what if dark energy changes? What if it's not constant? Some theories suggest dark energy might evolve, might weaken over time, or even reverse. If dark energy weakens enough, gravity might eventually overcome it. The expansion might slow, stop, reverse, and then the universe would start contracting. The Big Crunch. Every galaxy would start moving toward every other galaxy. Space would shrink. The universe would get smaller, denser, hotter. Eventually, all matter would be compressed back into an infinitely dense point. And then what? Maybe it bounces. Maybe the universe undergoes cycles of expansion and contraction. Big Bang, expansion, contraction, Big Crunch, Big Bang again. Over and over. Eternally. This is the cyclic universe model. Elegant. Appealing. But not supported by current observations. Dark energy shows no signs of weakening. If anything, it's constant or even strengthening. But we've only been observing dark energy for a few decades. Compared to the 13.8 billion year history of the universe, that's nothing. We're trying to predict the infinite future based on a cosmological eye blink of data. We could be wrong. Dark energy could change. The universe could reverse its expansion. Or something even weirder could happen. What if the vacuum itself is unstable? What if the quantum fields that permeate space could suddenly transition to a lower energy state? If that happened, a bubble of true vacuum would form. And it would expand at the speed of light, consuming everything in its path. Inside the bubble, the laws of physics would be different. Atoms might not be stable. Matter as we know it might not exist. This is called vacuum decay, or the bubble of death, or more formally, false vacuum decay. If the vacuum is unstable, and we don't know if it is, then someday, somewhere in the universe, it could decay. A bubble of true vacuum would form. And it would spread, destroying everything, rewriting the laws of physics, until it consumed the entire universe. We wouldn't see it coming. The bubble expands at the speed of light. By the time light from the bubble's edge reached us, the bubble itself would already be here. One moment you're reading this. The next moment, you and everything around you cease to exist as the fundamental structure of reality changes. Cheerful thought, right? But the probability of this happening in the next billion years is vanishingly small. If it were likely, it probably would have happened already. The universe is 13.8 billion years old. If vacuum decay were probable, we wouldn't be here to worry about it. So probably, we're safe from vacuum decay. Probably. But the fact that we even have to consider such scenarios shows how little we understand about the universe we're in. How tentative our knowledge is. How much we're still guessing. We don't know what 95% of the universe is made of. Dark matter and dark energy. We've named them, but we don't know what they are. Don't know where they come from. Don't know how they work. We don't know if the universe is infinite or finite. Don't know what happened in the first 10 to 43 seconds after the Big Bang. Don't know if other universes exist. Don't know the ultimate fate of our universe. We're like ants on a beach, trying to understand the ocean. We see the waves, feel the sand, measure the tides. But the depth? The vastness? The creatures living in the abyss? Beyond our comprehension. And yet, we keep trying. We build telescopes, particle colliders, gravitational wave detectors. We point them at the sky and into the atom. We collect data, build models, make predictions, test them, and slowly, inch by inch, we're figuring it out. We know the universe is 13.8 billion years old. We know it's expanding. We know it started in a hot, dense state. We know the proportions of hydrogen, helium, and lithium in the universe match the predictions of Big Bang nucleosynthesis. We know the cosmic microwave background matches the predicted afterglow of the Big Bang. We've seen galaxies at the edge of the observable universe as they were 13 billion years ago. We've detected gravitational waves from colliding black holes billions of light years away. We've measured the acceleration of cosmic expansion. We don't know everything, but we know something. And what we know is astonishing. The universe is expanding. Space itself is growing, creating more distance, more volume, more room for existence. And it's expanding without expanding into anything. Because it doesn't need to expand into anything. It's self-contained, self-creating, the ultimate container. Your brain rebels against this. Mine does too. We want edges, boundaries, containers, and outside. But the universe has no outside. It is all that exists. And it's enough. Let me hit you with one more perspective. One that might actually help. Think about the surface of the Earth. It's finite. About 510 million square kilometers. But it has no edge. No boundary. You can walk in any direction forever, if you could walk on water and never reach an edge. Never fall off. Never find a boundary. The surface just curves back on itself. It's finite but unbounded. Now imagine adding more surface area. The Earth grows larger. The radius increases. The surface area expands. But where does the new surface come from? It's not pushing into the interior of the Earth. The interior isn't empty space waiting to be filled. The interior is rock and metal. The surface is, well, the surface. An infinitely thin boundary. When the surface expands, new surface area is created. Intrinsically. Without taking space from anywhere else. This is analogous to the expansion of the universe. Except instead of a two-dimensional surface embedded in three-dimensional space, it's three-dimensional space embedded in, well, maybe four-dimensional space-time. Maybe higher dimensions. Maybe nothing at all. The expansion is intrinsic. New space is created. Not taken from somewhere else. Not pushing into pre-existing void. Just created. Where does it come from? The quantum fields. The vacuum energy. The dynamics of space-time itself. General relativity allows space to be dynamic. To grow. To shrink. To curve. To ripple. Space is not static. Not a fixed background. It's an active participant in the universe. It responds to matter and energy. It expands. It's alive, in a sense. And you're made of it. Your body is patterns of quantum fields in space-time. When you move, you're not moving through space. You're space-time reconfiguring itself. Creating a new pattern. A new arrangement. You are the universe localized. A temporary concentration of matter and energy in a particular configuration. A pattern that maintains itself for a while, 70, 80, maybe 100 years, and then dissolves back into the background. And the background itself? It's expanding, stretching, growing, taking you with it, taking everything with it. Right now, as you read this, you're moving away from distant galaxies at thousands of kilometers per second. Not because you're moving, because space itself is carrying you, expanding the distance, creating more room between you and them. You're riding the cosmic expansion, surfing on the fabric of reality as it grows. And you're doing it without going anywhere, without moving into anything, because there's nowhere to move into. Nothing outside. Just space creating more space, more distance, more universe. Forever. Or at least until the heat death, or the big rip, or vacuum decay, or whatever ending awaits us. But that's billions or trillions of years away. For now you're here, on this planet, in this galaxy, at this moment in cosmic history when the universe is still young enough to be interesting, still filled with stars and galaxies and planets and life. A brief, beautiful moment in the life of the cosmos. Before the long, cold night of entropy. But even that ending is magnificent in its own way. Terrifying, yes, but magnificent. The universe will end not with a bang but with a whimper. A slow fade out. Stars will exhaust their fuel. One by one, they'll wink out. Galaxies will grow dark. Black holes will evaporate via Hawking radiation, taking quadrillions of years to disappear. And in the end, all that will remain is a thin soup of photons and particles, spread so thinly across such vast distances that they might as well not exist. The temperature of the universe will approach absolute zero. Entropy will be maximized. Nothing will happen. Nothing can happen. The universe will be dead. Truly, completely, irreversibly dead. But here's the beautiful part: that's not happening now. Right now, the universe is alive, burning with the light of a trillion stars, filled with planets and moons and asteroids and comets, teeming with complexity and structure, and in at least one place we know of, life, and consciousness, and curiosity, and the ability to ask impossible questions like, what is the universe expanding into? You exist at a special time. A time when the universe is old enough to have created complex structures like stars and planets and brains, but young enough that those structures still exist, still burn, still think. Billions of years from now, no one will be around to ask these questions. The universe will be too cold, too empty, too dark. But you're here now, and you're asking, and you're understanding, at least a little bit, the impossible, terrifying, beautiful reality you're embedded in. The universe is expanding without expanding into anything. Because it doesn't need to. Because it is all there is. Because space creates itself. Because reality is self-contained and self-creating and utterly, completely sufficient. It makes no intuitive sense. It breaks your brain. It defies everything you think you know about containers and boundaries and edges. But it's true. Measured. Observed. Confirmed. And the fact that you, a collection of atoms that were forged in the hearts of dying stars, arranged into a pattern capable of thought and wonder and confusion, can contemplate this impossible truth? That's the real miracle. Not that the universe expands, but that it created beings capable of understanding that it expands. You are the universe looking at itself, trying to understand itself, succeeding against all odds. Your ancestors lived in trees. They picked fruit and avoided predators and had no idea about stars or galaxies or cosmic expansion. They didn't need to know. It didn't help them survive or reproduce. But their descendants, you, have pushed beyond survival, beyond reproduction, into the realm of pure understanding, pure curiosity, asking questions that have no practical value whatsoever but that satisfy something deep in the human spirit. The need to know, to understand, to see reality as it truly is, no matter how strange or counterintuitive. And what you've found is this: the universe is expanding. Space itself grows. Distance increases. And it's expanding without expanding into anything because it doesn't need to expand into anything. It's everything. All there is. All there ever was or will be. Self-contained. Self-creating. Infinite or finite, we don't know. Eternal or temporary, we're not sure. But definitely expanding. Definitely growing. Definitely creating more space, more distance, more room for existence. And you're riding that expansion. Right now. This very second. You and everything around you is being carried along on the greatest journey in existence. The cosmic expansion. The growth of reality itself. You're not expanding. Your atoms aren't getting farther apart. But the space between you and distant galaxies? That's growing. Millions of kilometers per second. Faster than light itself. And someday, billions of years from now, if anyone is still around to observe it, they'll see a universe vastly larger than the one we see today. Darker. Emptier. Colder. But also more spacious. More vast. More infinite, if that's possible. And maybe, just maybe, they'll still be asking the same question: what is it expanding into? And maybe, just maybe, they'll arrive at the same unsatisfying, true answer: nothing. Itself. The question doesn't make sense. Because the universe is all there is. And all there is enough. The universe doesn't need an outside, doesn't need a container, doesn't need permission or space or room to expand. It just expands. Because that's what universes do. Because the laws of physics say so. Because dark energy pushes. Because space-time is dynamic. It expands into nothing. Into itself. Into more universe. Forever. Or until it doesn't. But for now, for this brief, glorious moment in cosmic history, it expands. It grows. It creates more room for stars and galaxies and planets and life. More room for you. You are here because the universe expanded. Because it created space for stars to form. For planets to coalesce. For chemistry to complexify. For life to emerge. For consciousness to arise. You are a child of cosmic expansion. Born from the growth of space-time itself. And now you stand here, on this planet, at this moment, contemplating the very process that made your existence possible. The universe expanding. Creating more of itself. Without needing anything external. Without requiring an outside. Just growing. Just being. Just existing in the strange, impossible, beautiful way that it does. And you understand it. Or at least, you're trying to. You're wrapping your mind around the unwrappable. Comprehending the incomprehensible. And that, more than anything, is why you matter. Why consciousness matters. Why thought and curiosity and wonder matter. Because the universe, without you, is just stuff happening. Particles interacting. Fields fluctuating. Space expanding. But with you, with consciousness, the universe becomes aware of itself. Understands itself. Marvels at itself. You are the universe's way of knowing that it's expanding. Of understanding how. Of asking why. And even if the answer is strange and unsatisfying and impossible to visualize, you keep asking. Keep wondering. Keep pushing at the boundaries of knowledge. Because that's what conscious beings do. That's what humans do. We ask impossible questions. We seek uncomfortable truths. We stare into the abyss of our own ignorance and say, I want to know more. And slowly, painstakingly, we figure it out. We build models. Test them. Refine them. We point telescopes at the sky and particle accelerators at atoms. We measure and calculate and observe. And we learn. We learn that the universe is 13.8 billion years old. That it started in a hot, dense state. That it's been expanding ever since. That it's filled with mysterious dark matter and dark energy. That it's probably infinite. That it might be one of many. That it will likely end in cold, dark emptiness. We learn these things despite being tiny, fragile, short-lived creatures on an insignificant rock orbiting an average star in an unremarkable galaxy in a vast, expanding cosmos. We learn them because we must. Because curiosity drives us. Because understanding is its own reward. And what we learn shatters our intuitions, breaks our brains, shows us a universe far stranger than we imagined. A universe that expands without expanding into anything. That creates space from nothing. That might be infinite. That will eventually die. A universe that doesn't care if we understand it. That doesn't need our comprehension or approval. That just is. But we understand it anyway. Against all odds. Despite our limitations. Because we're human. Because we're curious. Because we're here. And that might be the most astonishing thing of all. Not that the universe expands. But that beings emerge within it capable of figuring that out. You are one of those beings. Right now. At this moment. Reading these words. Thinking these thoughts. The universe is expanding into nothing. Into itself. Into more universe. And you understand that. Or you're starting to. Despite it being impossible. Despite it defying intuition. Despite it making no sense to a brain evolved for completely different purposes. You understand. And that understanding is beautiful. Precious. Rare. Because most matter in the universe doesn't understand anything. Most atoms just exist. Most particles just interact. Most space just expands. But you're different. You're matter that thinks, atoms that wonder, space-time that contemplates itself. You are the universe understanding the universe, asking questions about itself, marveling at its own strangeness. And even though the answer to what is the universe expanding into is ultimately unsatisfying, nothing itself, the question is wrong. The fact that you can ask it, contemplate it, and partially understand it is profound. You are proof that the universe can understand itself, that matter can become conscious, that complexity can emerge from simplicity. You are a miracle, not in a supernatural sense, in a cosmic sense. The universe expanded, space grew, stars formed, planets coalesced, chemistry complexified, life emerged, evolution happened, brains developed, consciousness arose. And here you are, a pattern of atoms thinking about patterns of atoms, space-time contemplating space-time, the universe aware of itself. It took 13.8 billion years for this to happen, for matter to arrange itself into a configuration capable of understanding cosmic expansion. But it happened. You happened. And you're here, right now, grappling with one of the deepest questions in existence. What is the universe expanding into? And the answer, as strange and unsatisfying as it is nothing. It doesn't need to expand into anything. It just expands. Because that's what space does. That's what reality does. It grows, creates more of itself, without requiring permission or space or an outside. The universe is self-contained, self-creating, sufficient unto itself. And you, improbable as it seems, are part of that. A small part, a temporary part, but a part nonetheless. You are the universe, localized, conscious, curious, and the universe is expanding, taking you with it, creating more space around you, more distance, more room, expanding into nothing, into itself, into more universe, forever. And you're here to witness it, to understand it, to marvel at it, despite the impossibility, despite the strangeness, despite the vertigo-inducing confusion of trying to imagine space expanding without expanding into anything. You're here. You're thinking. You're understanding. And that, perhaps, is the most beautiful thing in this expanding, self-creating, impossible universe. Not that it expands, but that you can know it does. Let me give you something even more terrifying to consider. Every atom in your body right now is traveling through time at a different rate than atoms in a distant galaxy. Time itself is not constant across the universe. It's not flowing at the same rate everywhere. General relativity tells us that gravity warps time. Strong gravitational fields slow time down. Weak gravitational fields speed it up. You're sitting in Earth's gravitational field. Time flows at a certain rate for you. But an astronaut on the International Space Station? Time flows slightly faster for them. About 0.01 seconds faster per year. GPS satellites have to account for this. Their clocks run faster than clocks on Earth's surface because they're farther from Earth's gravity well. If we didn't correct for this time dilation, GPS would be off by several kilometers within a single day. Now think about a galaxy 10 billion light-years away. The gravitational environment there is completely different. The local galaxy cluster, the nearby supermassive black holes, the density of dark matter, all of it affects how time flows. What does, now, even mean when time flows at different rates in different parts of the universe? When you look at a distant galaxy and say, "That's what it looks like now," you're wrong. That's what it looked like billions of years ago when the light left. But even if you could see it, now, accounting for light travel time, what does now mean? Their now and your now are not synchronized. Cannot be synchronized. There is no universal now. No cosmic clock ticking at the same rate everywhere. Time is local, relative, flexible. And here's where it gets truly impossible to grasp. The expansion of space itself affects time. Space and time are not separate things. They're unified into space-time. When space expands, it's not just distance increasing. It's the entire metric of space-time changing. Time is part of that metric. In the early universe, when space was compressed, time flowed differently than it does now. The rate of causality, the speed at which cause and effect propagate, was different. Physicists describe the early universe in terms of temperature and energy density, not time. Because time as we understand it barely applies. The first 10 to 43 seconds after the Big Bang, the Planck epoch, is a complete mystery. Our physics breaks down. Time loses meaning. Quantum mechanics and general relativity both fail. We literally cannot describe what happened. Cannot calculate it. Cannot model it. The math gives infinities and nonsense. Space and time are so warped, so quantum, so chaotic that our best theories simply don't work. It's like trying to divide by zero. The equations explode. Give no answers. Or infinite answers. Which is the same as no answers. We know the universe was unimaginably hot. Unimaginably dense. But hot and dense are understatements so vast they're meaningless. All the energy that would eventually become every star, every galaxy, every planet, every atom in your body, all of it compressed into a region smaller than a proton. The temperature was 10 to 32 Kelvin. That's a 1 followed by 32 zeros. Kelvin. For reference, the core of the Sun is 15 million Kelvin. The entire observable universe today has an average temperature of 2.7 Kelvin. But in the first moments? 10 to 32 Kelvin. A temperature so high that atoms couldn't exist. Nuclei couldn't exist. Protons and neutrons couldn't exist. Even quarks couldn't exist as separate particles. Everything was a unified quark-gluon plasma. A soup of fundamental particles and forces so hot that they were essentially indistinguishable. The four fundamental forces we know today, gravity, electromagnetism, strong nuclear force, weak nuclear force, they were unified. A single force. A single interaction. Physicists call it the Grand Unified Theory, though we haven't actually figured out what that theory is yet. As the universe expanded and cooled, this unified force broke apart. First gravity separated. Then the strong nuclear force. Then electromagnetism and the weak nuclear force split. Each separation released enormous amounts of energy. Each phase transition reshaped the universe. Changed the rules. Changed what was possible. After about 10 to 6 seconds, 1/1,000,000th of a second, the universe had cooled enough for quarks to combine into protons and neutrons. After about 1 second, it was cool enough for nuclear fusion to begin. Protons and neutrons fused into helium nuclei. This period lasted about 3 minutes. In those 3 minutes, about 25% of all the hydrogen in the universe was fused into helium, along with trace amounts of lithium and beryllium. Then the universe expanded too much. Cooled too much. The density dropped. Fusion stopped. And it wouldn't start again for hundreds of millions of years, when the first stars formed. But here's the critical point: all of this, the phase transitions, the cooling, the fusion, happened because space was expanding. Space expansion was creating more volume, diluting the energy density, lowering the temperature, allowing particles to slow down enough to interact, to combine, to form structures. Without expansion, the universe would have remained an infinitely hot, infinitely dense singularity. No atoms. No stars. No you. Expansion made complexity possible. Made chemistry possible. Made life possible. You exist because space expanded into nothing. But let's go deeper into what nothing means. Because even nothing is something in quantum mechanics. The Heisenberg uncertainty principle tells us that you cannot simultaneously know the position and momentum of a particle with perfect precision. The more accurately you measure one, the less accurately you can know the other. This isn't a limitation of measurement technology. It's a fundamental property of reality. Particles don't have definite positions and momenta simultaneously. They exist in a quantum superposition of possibilities. And this has a bizarre consequence: empty space cannot be truly empty. If empty space had zero energy, zero particles, zero everything, then we'd know its energy precisely. Zero. But the uncertainty principle forbids us from knowing energy that precisely. There must be fluctuations, uncertainties, temporary violations of energy conservation. These violations manifest as virtual particles. Particle-antiparticle pairs that spontaneously appear, exist for a fleeting moment, then annihilate each other and disappear. An electron and a positron pop into existence. They live for about 10 to 21 seconds. Then they collide and vanish in a flash of energy. This happens everywhere. All the time. Throughout all of space. Empty space is seething with these quantum fluctuations. Roiling with virtual particles that exist and then don't exist in an endless, chaotic dance. And these virtual particles have measurable effects. The Casimir effect: place two metal plates very close together in a vacuum. Virtual particles with wavelengths larger than the gap between the plates cannot form between them. But they can form outside. This creates a pressure difference. The plates are pushed together by the quantum vacuum. We've measured this. It's real. Virtual particles are real, in a sense. They're not just mathematical artifacts. They have physical consequences. So when the universe expands, creating more space, it's creating more quantum vacuum. More room for virtual particles to fluctuate. More volume for the quantum fields to inhabit. The universe isn't expanding into empty nothingness. It's expanding into quantum nothingness, which is a different kind of thing entirely. And quantum nothingness might be unstable, might decay, might suddenly transition into a different state, rewriting the laws of physics throughout the universe in an expanding bubble of doom traveling at the speed of light. This is the vacuum decay scenario I mentioned before. But let's dig into why it's possible. Why physicists take it seriously. The standard model of particle physics describes particles as excitations of quantum fields. The electron field, the quark field, the photon field. These fields permeate all of space. Always. Everywhere. Each field has a ground state. The lowest energy configuration. The vacuum state. When a field is in its vacuum state, no particles are present. The field is empty, but still there. Still existing. Still ready to be excited into particles if you add energy. Now, here's the problem. We don't know if the vacuum states of these fields are the true ground states. The absolute lowest energy. Or if they're false vacuums. Local minima. Temporarily stable but not truly stable. Think of a ball resting in a shallow valley on a hillside. It's stable. If you nudge it slightly, it rolls back. But if you push it hard enough, it could roll over the lip of the valley and tumble down the hill into a deeper valley. The true lowest point. The shallow valley is a false vacuum. Temporarily stable but not the true ground state. If our universe's quantum fields are in false vacuum states, they could tunnel to the true vacuum. Quantum tunneling allows particles and fields to pass through energy barriers they shouldn't classically be able to cross. If a small region of space tunnels to the true vacuum, a bubble forms. Inside the bubble, the field is in a lower energy state. The excess energy is released, powering the bubble's expansion at the speed of light. And inside the bubble, physics is different. Particle masses change. Force strengths change. Maybe atoms can't form. Maybe matter disintegrates. We don't know. Because we don't know what the true vacuum looks like. We don't even know if there is a true vacuum different from the one we're in. But the possibility exists. And it's utterly terrifying. Because if it happens, we have no warning. No way to stop it. No escape. The bubble expands at light speed. We'd see it coming at the same moment it arrives. Our doom traveling on the same light waves that would warn us of it. One instant you're reading this. The next instant, the fundamental structure of reality changes and you cease to exist. But again, probably not going to happen. Probably. The universe has existed for 13.8 billion years. If vacuum decay were likely, it probably would have occurred by now. Unless we're just unlucky. Unless the bubble is already racing toward us from a billion light years away. We wouldn't know. Sweet dreams. Let's shift to something slightly less apocalyptic, the cosmic microwave background. This is the oldest light in the universe. The afterglow of the Big Bang. Light that has been traveling through space for 13.8 billion years, arriving at your eyes right now. Well, not your eyes. It's microwave radiation. You can't see it. But radio telescopes can detect it. And it's everywhere. Every cubic centimeter of space is filled with this ancient light. The cosmic microwave background, CMB, was released about 380,000 years after the Big Bang. Before that, the universe was opaque. Too hot. Too dense. Photons couldn't travel freely. They'd scatter off electrons almost immediately. But after 380,000 years, the universe had cooled to about 3,000 Kelvin. Cool enough for electrons and protons to combine into hydrogen atoms. Neutral atoms don't scatter light as effectively as free electrons. Suddenly, photons could travel freely through space. This moment is called recombination. And the light released at that moment is what we detect today as the CMB. Except it's not 3,000 Kelvin anymore. It's 2.7 Kelvin. The expansion of the universe has stretched the light. Redshifted it. Cooled it. What was visible light 13.8 billion years ago is now microwave radiation. The CMB is incredibly uniform. Almost exactly the same temperature in every direction. 2.725 Kelvin. Variations are only about 1 part in 100,000. Tiny fluctuations. Slightly warmer or cooler patches. But those tiny fluctuations are the seeds of everything. Regions that were slightly denser. Slightly warmer. Those regions had slightly stronger gravity. They attracted more matter. Over millions of years they grew. Collapsed. Formed the first stars. The first galaxies. Every structure in the universe today, galaxies, clusters, superclusters, grew from those tiny quantum fluctuations in the early universe. Amplified by gravity over billions of years. You can see the baby pictures of galaxies in the CMB. The places where the Milky Way would eventually form. Where Andromeda would form. Where billions of galaxies would eventually emerge. All encoded in temperature variations of 1 part in 100,000. And here's the truly mind-bending part. Those fluctuations came from quantum uncertainty. During inflation, quantum fluctuations in the inflaton field were stretched to cosmic scales. Tiny, random quantum events became the seeds of galaxies. The largest structures in the universe, superclusters spanning hundreds of millions of light years, originated from quantum fluctuations smaller than a proton. Quantum mechanics, operating on the smallest scales, shaped the universe on the largest scales. Your existence traces back to a quantum fluctuation 13.8 billion years ago. A random event. A roll of the cosmic dice. That fluctuation led to a slightly denser region, which led to a galaxy forming, which led to stars forming, which led to planets forming, which led to life emerging, which led to you. If that quantum fluctuation had been slightly different, you wouldn't exist. The galaxy you're in wouldn't exist. Earth wouldn't exist. Everything you are, everything you know, everyone you love, all contingent on a quantum accident in the first fraction of a second after the Big Bang. Does that make your existence meaningless? Or infinitely precious? I'd argue the latter. You are the universe's unlikely gift to itself. A chance configuration of atoms that can think and feel and wonder. Against astronomical odds, you exist. And you're here contemplating the expansion of space-time into nothing. Trying to wrap your mind around concepts that break intuition. Pushing against the limits of human comprehension. That's not meaningless. That's beautiful. But let's return to the expansion. Because there's another layer of strangeness we haven't explored. The expansion isn't smooth. On small scales, solar systems, galaxies, even galaxy clusters, gravity dominates. These structures aren't expanding. They're bound together by their mutual gravitational attraction. Earth isn't getting farther from the Sun. The Sun isn't getting farther from the center of the Milky Way. The Milky Way and Andromeda are actually approaching each other. It's only on the largest scales, between galaxy clusters and superclusters, that expansion dominates. The universe is like a foam, or a sponge. Galaxies cluster along filaments and sheets. These structures, the cosmic web, don't expand. They're held together by gravity. But the voids between them? Those are expanding, growing, creating more emptiness, more separation between the filaments. So the universe isn't uniformly expanding. It's expanding in some places and not others. The voids grow. The structures stay roughly the same size. Over time, this means the universe becomes more spread out, more diffuse. The structures remain, but they're separated by ever larger voids. Like raisins in an expanding loaf of bread. The raisins don't expand, but the bread does. So the distance between raisins increases. Eventually, trillions of years from now, the voids will be so large that galaxies in one filament cannot see galaxies in another. The light won't have time to cross the ever-expanding void. Civilizations in different filaments will be cosmically isolated. They'll have no evidence that other structures exist. They'll think they're alone in a small, finite universe surrounded by infinite emptiness. And they'll be wrong. But they'll have no way to know they're wrong. We're lucky. We live in an era when the universe is still connected, still observable. We can see the CMB. We can see distant galaxies. We can map the cosmic web. But that window is closing. Every second, more of the universe becomes permanently unobservable. Sliding beyond our cosmic event horizon. The universe is forgetting itself, erasing its own history, separating into isolated pockets that can never communicate, never interact, never know about each other. Entropy isn't just increasing, it's fragmenting the universe, breaking it apart into causally disconnected regions. Each region might as well be its own separate universe. The multiverse might not require eternal inflation or quantum many-worlds. Simple cosmic expansion, given enough time, will create a multiverse. A collection of causally disconnected regions, each unaware of the others. Each alone in an expanding void. This is the true loneliness of the cosmos. Not that we might be the only intelligent life, but that even if we're not, we might be fundamentally incapable of ever reaching them, ever knowing them, ever communicating. The speed of light is finite. Space is expanding. There are places in the universe we can never reach. Beings we can never meet. Galaxies we can never visit. Not because we lack technology. Because the laws of physics forbid it. The expansion is too fast. The distance is too great. The cosmic horizon too close. We are prisoners of our local region of space-time. Trapped inside an ever-shrinking observable universe, watching more and more of reality disappear beyond the horizon. Forever. Unless faster-than-light travel is possible. Unless wormholes can be created. Unless the laws of physics have loopholes we haven't discovered. But probably not. Probably we're stuck. Probably the observable universe will keep shrinking until all we can see is our local galaxy group. And then nothing. That's the future. Trillions of years from now. Darkness. Isolation. Entropy. But it's also weirdly comforting. Because it means right now, this moment, is special. The universe is still young. Still bright. Still connected. You can look up at the night sky and see light from billions of years ago. From billions of light years away. You can see the history of the cosmos written in starlight. That's a gift. A temporary gift. An accident of being born at the right time in cosmic history. Before the long night. Before the isolation. You're here during the universe's bright age. Its age of connection. Its age of discovery. Enjoy it. Marvel at it. Because it won't last. Nothing lasts. Not stars. Not galaxies. Not even space-time itself might last, depending on which theory of quantum gravity is correct. Some theories suggest space-time is emergent, not fundamental. that it arises from something deeper, more fundamental, a quantum information substrate, or quantum entanglement, or something we haven't even conceived of yet. If space-time is emergent, then asking what the universe is expanding into is like asking what a computer program is running in. The program exists in the computer's memory, the computer's processor, but the program itself doesn't know about that substrate. It just runs, operates according to its own internal logic. Maybe the universe is similar. Maybe space-time is a useful description of reality at macroscopic scales. But at the deepest level, reality is something else entirely. Something that doesn't include space or time as fundamental concepts. And if that's true, then the expansion of space is just an emergent phenomenon, a consequence of deeper processes, not a fundamental feature of reality. This is highly speculative. We have no evidence for emergent space-time, but it's an active area of research. Physicists are exploring whether space-time might arise from quantum entanglement, from information theory, from holographic principles. The holographic principle is particularly wild. It suggests that all the information in a three-dimensional region of space can be encoded on its two-dimensional boundary. Like a hologram, the interior is redundant, secondary. The boundary contains everything. If this is true, then maybe the universe doesn't have an interior at all. Maybe we're living on the surface of something. A two-dimensional surface that appears three-dimensional to us because of how information is encoded and decoded. This sounds insane, and it might be wrong, but it's consistent with black hole thermodynamics, with string theory, with several approaches to quantum gravity. And if it's true, then the question, what is the universe expanding into, becomes, what is the surface expanding on? And the answer might be nothing. Because the surface is all there is. The interior is illusory. A projection. A hologram. You might be a hologram. I might be a hologram. Everything might be information encoded on a distant boundary, creating the illusion of a three-dimensional universe expanding through time. This is the kind of thing that makes physicists' brains hurt. That makes them question whether they should have studied literature instead. But it's a serious proposal, with serious mathematical backing. It might be how reality actually works. Or it might be completely wrong. We don't know. We won't know for decades. Maybe centuries. Maybe never. Because testing these ideas requires energies we can't reach. Experiments we can't perform. Observations we can't make. We're limited by the size of our particle colliders, by the sensitivity of our telescopes, by the fundamental constraints of being inside the universe we're trying to understand. We can't see the universe from outside, can't measure its boundary, can't confirm whether space-time is fundamental or emergent. We're like characters in a video game trying to figure out the programming language the game is written in. We can observe the rules, the patterns, the consistencies, but we can't see the underlying code, can't access the hardware it's running on. We're trapped in the simulation, if you want to use that metaphor. Not that the universe is literally a simulation, but that we're fundamentally limited in what we can observe and measure about reality from inside. So when we ask, what is the universe expanding into? We're asking a question that might not have an answer we can access. The answer might exist, but it might be outside our observable, measurable, comprehensible reality. Like asking what's north of the North Pole. The question is grammatically correct, but it doesn't have a meaningful answer within the framework of Earth's geometry. Similarly, what is the universe expanding into? Might not have a meaningful answer within the framework of physics as we understand it. The universe might just be expanding. Period. Full stop. No further explanation possible or necessary. And you might find that unsatisfying, frustrating, incomplete. Join the club. Every physicist feels the same way. But here's the thing, that frustration drives discovery, drives curiosity, drives the search for deeper understanding. If we had all the answers, science would be over. There'd be nothing left to discover. No mysteries to solve. no questions to ask. The fact that we don't fully understand cosmic expansion means there's more to learn, more to discover, more frontiers to push. And that's exciting. That's what makes physics worth doing. The unknown, the mysterious, the incomprehensible. We stand on the shores of the cosmic ocean, to paraphrase Carl Sagan. We've waded in. We've gotten our feet wet. We've discovered that the ocean is deep, vast, strange. But we haven't explored its depths, haven't mapped its contours, haven't found all its creatures. There's more out there, waiting, hidden in the mathematics, encoded in the observations, lurking in the data. Dark matter, dark energy, quantum gravity, the ultimate fate of the universe, the nature of space-time itself. All mysteries, all unsolved, all calling to us. And you're part of that. Part of the generation that might solve some of these mysteries. Or at least push the frontier a little farther. Understand a little more. Because humans are explorers. Curious. Restless. Never satisfied with. We don't know. We want to know. Need to know. We'll keep pushing until we do know. Or die trying. And that drive, that curiosity, that refusal to accept ignorance, that's what makes humanity special. What makes consciousness valuable. What makes you important. You're not just a passenger in this expanding universe. You're an explorer, a discoverer, a seeker of truth. The universe is expanding into nothing, into itself, into incomprehensibility. And you're here, trying to comprehend it anyway. That's the miracle. That's the meaning. That's why you matter. Not because the universe needs you. It doesn't. It expanded for 13.8 billion years before you existed and will continue expanding for trillions more after you're gone. But because you're here now. Aware. Conscious. Thinking. Questioning. Understanding. You're the universe waking up. Opening its eyes. Looking at itself in the mirror and asking, what am I? How do I work? What am I expanding into? And even though the answers are strange and incomplete and maybe ultimately inaccessible, you keep asking. That persistence. That curiosity. That refusal to accept mystery without investigation. That's what makes you human. That's what makes you matter. The universe is expanding into nothing. But you're here, expanding your understanding. Pushing your comprehension. Growing your awareness. And that growth, that expansion of consciousness and knowledge, is its own kind of miracle. Perhaps the only miracle. In a universe governed by physics, where everything reduces to particles and forces and fields, consciousness remains inexplicable. Mysterious. Special. You are matter that knows its matter. Atoms that understand their atoms. The universe comprehending itself. That's impossible. And yet here you are. Doing it. So yes, the universe is expanding into nothing. But you're expanding into understanding. And that makes all the difference. The cosmic microwave background has another secret embedded in it that will shatter your sense of direction. Those tiny temperature fluctuations, 1 part in 100,000, they're not random. They have patterns, correlations, structure. And one of those structures is called the axis of evil. No, really. That's what astronomers call it. A preferred direction in the universe. An alignment of the largest scale temperature fluctuations in the CMB that all seem to point the same way. This should be impossible. The cosmological principle, one of the foundations of modern cosmology, states that the universe is isotropic. The same in all directions. No preferred orientation. No cosmic up or down. No axis. No pole. But the axis of evil suggests otherwise. The quadrupole and octupole moments of the CMB, the largest scale fluctuations, are aligned with each other. And they're aligned with the plane of the solar system. And the equinox. What are the odds of that? Astronomically small. It should be random. Pointing in any direction. But it's not. Some scientists think it's a statistical fluke. An artifact of our limited view. We only see one universe, one realization of cosmic history. Maybe we just got unlucky. Drew a weird hand from the cosmic deck. Others think it's evidence of something deeper. Maybe the universe isn't isotropic. Maybe there's a preferred direction, a rotation, an asymmetry we haven't accounted for. Or maybe it's evidence that our universe is finite, smaller than we thought, with a specific topology, shape, boundary conditions that create these alignments. We don't know. The axis of evil remains unexplained, a cosmic mystery written in the oldest light in the universe. And it's not the only anomaly in the CMB. There's also the cold spot, a region about 1.8 billion light-years across that's significantly colder than the surrounding areas. About 70 microkelvins colder. That might not sound like much, but it's a 3.3 sigma deviation from predictions. That means there's only about a 0.1% chance it's random noise. So what is it? One possibility, it's a supervoid, an enormous empty region of space with much lower density than average. Light passing through this void would experience a slight energy loss, the integrated Sachs-Wolf effect, making it appear colder. But the void would have to be enormous, about 1.8 billion light-years across. That's at the upper limit of what structure formation models predict. Maybe even beyond that limit. Another possibility, it's a window into another universe. In multiverse theories, other bubble universes might have collided with ours. The collision would leave an imprint, a bruise in the CMB, a cold spot where the two bubbles touched. This sounds like science fiction, but it's testable. Collisions would create specific patterns in the CMB, concentric circles of temperature variations. We've looked for these patterns, haven't found them yet. But absence of evidence isn't evidence of absence. Maybe we haven't looked carefully enough. Maybe the collision happened in a region we can't see, beyond our observable universe. Or maybe the cold spot is just a statistical fluctuation. Bad luck. Cosmic randomness producing a weird result. We won't know until we gather more data, build better telescopes, map the CMB with higher precision. But here's what keeps me awake at night. What if these anomalies, the axis of evil, the cold spot, others we haven't even discovered yet, what if they're telling us that our entire cosmological model is wrong? What if the universe isn't homogeneous and isotropic? What if it has structure and direction and asymmetry on the largest scales? What if we've been making a fundamental assumption that doesn't hold? The cosmological principle is just that, a principle, an assumption. We assume it because it makes the math tractable, because it matches most observations, because without it, cosmology becomes impossibly complicated. But what if it's wrong? What if the universe has a center after all? A direction? A shape? A topology we haven't imagined? Then everything changes. Our distance measurements, our age estimates, our understanding of expansion, all based on assumptions that might be false. We might be living in a universe completely different from the one we think we're in. And we wouldn't even know it, because we're trapped inside, looking out through a keyhole, trying to reconstruct the entire room from the limited view. Let's talk about something even more disturbing, the Hubble tension. Remember the Hubble constant? The rate at which the universe is expanding? 70 kilometers per second per megaparsec? Well, that's one measurement, derived from observing nearby galaxies and supernovae. Direct measurements of how fast things are moving away from us. But when we calculate the Hubble constant from the CMB, from the physics of the early universe, we get a different number. About 67 kilometers per second per megaparsec. 3 kilometers per second difference. Doesn't sound like much, but it's a 5 sigma discrepancy. That means there's less than 1 in a million chance it's random error. Something is wrong. Either our measurements are off, or our understanding is incomplete, or the universe is stranger than we thought. Maybe dark energy is evolving, getting stronger over time. That would make nearby measurements higher than CMB predictions. Maybe there's another component we haven't discovered. A new field. A new force. something affecting expansion in ways we don't understand. Maybe the early universe was different than we think. Maybe our CMB analysis is based on incorrect assumptions. Or maybe, and this is the truly terrifying possibility, maybe general relativity is wrong. Not completely wrong. It works incredibly well for most situations. But maybe on cosmic scales over cosmic times, it breaks down. Needs modification. Several physicists have proposed modified gravity theories. Mond, Tevis, FR gravity. These theories tweak Einstein's equations to match observations without requiring dark matter or dark energy. But they introduce new problems, new inconsistencies. They work in some contexts and fail in others. No modified gravity theory has successfully explained all observations better than general relativity plus dark matter plus dark energy. But that doesn't mean they're wrong. Just incomplete. Maybe we haven't found the right modification yet. And if general relativity needs modification on cosmic scales, then our understanding of cosmic expansion might be fundamentally flawed. The universe might not be expanding the way we think it's expanding. The acceleration might be an illusion created by our flawed equations. Dark energy might not exist at all. We might be completely, utterly, embarrassingly wrong about the most basic fact of modern cosmology. That possibility haunts every cosmologist. Keeps them checking and rechecking their calculations. Looking for errors. Alternative explanations. Anything that might resolve the tension without overturning everything. Because overturning everything means decades of work wasted. Entire careers built on sand. A collective delusion spanning generations of scientists. Nobody wants that. But the universe doesn't care what we want. It is what it is. And if we're wrong, we're wrong. The only way forward is more data, better measurements, more precise observations, and the intellectual honesty to admit when we've made a mistake. Science is self-correcting. Eventually. But it can take time. Sometimes centuries. Phlogiston. The luminiferous ether. Steady-state cosmology. All wrong. All eventually overturned by better observations and theories. Maybe dark energy will join that list. Maybe in 100 years, scientists will look back and laugh at our primitive 21st century cosmology. Our quaint belief in an expanding universe. Our naive trust in general relativity. Or maybe we're right. Maybe dark energy is real. Maybe the universe is expanding exactly as we think. Maybe the Hubble tension is just a measurement error that will be resolved with better instruments. We'll find out. Eventually. When the James Webb Space Telescope finishes its observations. When the next generation of CMB satellites launch. When gravitational wave detectors become sensitive enough to probe the early universe. The truth is out there. Written in starlight. Encoded in gravitational waves. Hidden in the quantum fluctuations of the CMB. We just have to read it. Carefully. Honestly. Without bias or preconception. And accept whatever it tells us. Even if it shatters everything we thought we knew. Now let's talk about what happens at the boundary. The edge of the observable universe. Not the edge of the universe. The universe might be infinite. But the edge of what we can observe. The cosmic horizon. 46.5 billion light-years away in every direction. Beyond that horizon, light hasn't had time to reach us yet. Or rather, light that started traveling toward us from beyond the horizon will never reach us because space is expanding too fast. But here's the question that should bother you. What's happening there? Right at the edge? Where space transitions from observable to unobservable? Is there a discontinuity? A boundary? A wall? No. Of course not. There's nothing special about that location. It's just empty space. Or rather, space filled with the same quantum fields and dark energy and occasional atoms as everywhere else. The cosmic horizon isn't a physical boundary. It's an informational one. A limit on what we can observe. Not on what exists. An observer in a galaxy beyond our horizon sees their own horizon. Their own observable universe. And from their perspective, we're beyond their horizon. They can't see us, can't know we exist. Every point in space has its own observable universe, its own horizon, and those horizons overlap. Create a complicated network of who can observe what, who can communicate with who is causally connected to whom. And as the universe expands, those horizons change. Galaxies currently within our horizon will eventually cross beyond it. Forever. Where do they go? They don't go anywhere. They just recede faster than light can travel. The space between us expands so much that light can no longer bridge the gap. They're still there. Still existing. Still doing whatever galaxies do. But we can never observe them. Never interact with them. Never know what happens to them. They effectively cease to exist for us. Not physically, but informationally, causally. If a galaxy crosses the cosmic horizon and we can never observe it again, does it still exist? Philosophically, this is the tree falling in the forest. Ontology versus epistemology. Being versus knowing. Physically, it doesn't matter. The galaxy doesn't care if we observe it. Doesn't cease to exist just because we can't see it anymore. But for us? For our understanding of the universe? For our scientific models and theories? It might as well not exist. Science is built on observations, measurements, data. If something cannot be observed, even in principle, it's not part of science. It's metaphysics. And as the universe expands, more and more of it transitions from physics to metaphysics. From observable to unobservable. From knowable to unknowable. The domain of science shrinks. The domain of metaphysics grows. Until eventually, trillions of years from now, almost nothing is observable. Almost everything is beyond the horizon. Future scientists will have almost no data. No distant galaxies to observe. No CMB to measure. No cosmological evidence. They'll be forced to theorize, speculate, philosophize, without observational constraints. Will they figure out that the universe is larger than what they can see? That it's expanding? That it began in a Big Bang? Maybe. If they're clever. If they can infer cosmic history from local observations. From the abundances of elements. From the structure of galaxies. From first principles. Or maybe not. Maybe they'll develop completely different theories. Wrong theories. Theories that match their limited observations but miss the bigger picture. We're lucky. We live in an era of abundance. Of observational riches. We can see billions of galaxies. Measure the CMB. Detect gravitational waves. Probe the early universe. But that abundance is temporary. The universe is giving us a window of opportunity. A brief moment in cosmic history when the evidence is still accessible. We need to use it. Gather as much data as we can. Answer as many questions as possible. Before the window closes. Because it's closing. Every second. Irreversibly. The universe is not just expanding. It's forgetting. Erasing its own history. Separating into disconnected pockets that can never communicate. And we're racing against that expansion. Trying to learn everything we can before it's too late. This is the urgency behind modern cosmology. Behind billion-dollar telescopes and satellite missions. Behind the frenetic pace of discovery. We have a finite time to figure out the universe. And that time is running out. Not in our lifetimes. Not in our children's lifetimes. But cosmologically speaking, the clock is ticking. Let's talk about quantum entanglement and its relationship to cosmic expansion. Because this is where things get truly weird. Quantum entanglement is a phenomenon where two particles become correlated in such a way that measuring one instantly affects the other, no matter how far apart they are. Einstein called it spooky action at a distance. He hated it. Thought it violated relativity. Thought it required faster-than-light communication. But it doesn't. Entanglement doesn't transmit information. You can't use it to send signals. The correlations are statistical. Probabilistic. Only visible when you compare measurements afterward. So relativity is safe. No faster-than-light communication. No causality violations. But here's the question: what happens to entangled particles when cosmic expansion separates them? When they're in galaxies receding from each other faster than light? Are they still entangled? Can quantum correlations survive cosmic expansion? The answer is complicated. Entanglement is fragile. Any interaction with the environment, decoherence, destroys it. Particles constantly interact with photons, other particles, fields. These interactions break entanglement almost instantly. So, for practical purposes, entanglement only survives in carefully controlled laboratory conditions. Isolated systems. Extreme cold. Shielding from interference. In the wild universe, entanglement is destroyed almost immediately. Particles become disentangled within nanoseconds or less. But let's imagine a thought experiment. Two particles are entangled, then immediately separated, placed in galaxies receding from each other, perfectly isolated from all environmental interactions, magically preserved in their entangled state. As space expands between them, are they still entangled? Quantum mechanics says yes. Entanglement is non-local. Doesn't depend on distance. The quantum state describes both particles together. A single wave functions spanning multiple locations. But general relativity says, well, it's complicated. Once the particles are separated by more than the cosmic horizon, they're in causally disconnected regions. Information cannot pass between them. Not even quantum information. So what happens? Some physicists argue that entanglement across cosmic horizons must be broken. That causality requires it. That quantum correlations cannot survive space-time disconnection. Others argue that entanglement is fundamental. More fundamental than space-time itself. That correlations persist even when classical communication is impossible. This isn't just academic. It relates to the holographic principle, to quantum gravity, to the nature of space-time emergence. If entanglement can span cosmic horizons, then maybe space-time isn't as fundamental as we think. Maybe it's an emergent phenomenon arising from quantum correlations. And those correlations are the real substrate of reality. This is the ER equals EPR conjecture, proposed by Juan Meldacena and Leonard Susskind. It suggests that entanglement and wormholes are the same thing. That entangled particles are connected by microscopic Einstein-Rosen bridges. Tiny wormholes stitching space-time together. If true, this would be profound. It would mean that space itself is made of entanglement. That geometry emerges from quantum information. And it would mean that asking, what is space expanding into, is the wrong question. Because space isn't a thing. It's a description of quantum correlations, of entanglement patterns. And as those patterns evolve, we perceive it as expansion, as distance increasing, as the universe growing. But really, it's just quantum information rearranging itself. Entanglement being redistributed. The network of correlations changing topology. This is deeply speculative. We have no direct evidence for ER equals EPR. No way to test it with current technology. But it's a beautiful idea. Elegant. Unifying. Potentially revolutionary. And it might be how the universe actually works. Or it might be completely wrong. Just another brilliant idea that doesn't match reality. We'll find out. Eventually. When we develop a working theory of quantum gravity. When we can calculate how entanglement behaves in curved space-time. When we can test these predictions observationally. But that's decades away. Maybe centuries. Maybe never. In the meantime, we're left with mysteries. Questions. Possibilities. The universe is expanding. Or the quantum information network is evolving. Or both. Or neither. We don't know. We just see the effects. Galaxies receding. Space growing. Distance increasing. And we try to understand why. How. What it means. That's the human project. Making sense of an incomprehensible universe. Finding patterns. Building models. Testing predictions. Sometimes we succeed. Sometimes we fail. But we never stop trying. Because that's what consciousness does. It asks questions, seeks answers, refuses to accept mystery as final. The universe is expanding into nothing, or into quantum entanglement, or into higher dimensions, or into something we haven't even conceived of yet. And you're here thinking about it, trying to understand it, pushing your comprehension to the breaking point. That's the miracle, not the expansion, but your awareness of it, your curiosity about it, your refusal to simply accept it without understanding, your matter interrogating matter, space-time questioning space-time, the universe demanding answers from itself. And that's beautiful, precious, rare, because most of the universe doesn't care, doesn't think, doesn't ask. But you do, and that makes all the difference. Consider the quantum foam. At the Planck scale, 10 to minus 35 meters, space-time itself becomes grainy, discontinuous, chaotic. At this scale, quantum uncertainty dominates completely. Space and time lose their classical meanings. Geometry itself fluctuates wildly. Wormholes open and close. Tiny black holes form and evaporate. Virtual particles swarm in impossible densities. This is the quantum foam, the substrate beneath reality, the churning chaos from which smooth space-time emerges at larger scales. And here's what should terrify you. When the universe expands, it's creating more quantum foam, more Planck-scale chaos, more microscopic wormholes, more quantum fluctuations. Every cubic centimeter of new space that comes into existence brings with it this roiling quantum substrate, this foam of possibility and uncertainty. Where does it come from? How does quantum foam spontaneously appear? The energy comes from the gravitational field, from the negative gravitational potential energy of the universe itself. Gravity can create matter and energy because gravitational energy is negative. The more gravitationally bound a system is, the more negative its energy. When you create new space, you're reducing the binding energy, making the total gravitational potential less negative. And that difference, that energy, manifests as new quantum fields, new vacuum energy, new foam. It's like borrowing money from a bank with negative interest rates. The more you borrow, the richer you get. Except instead of money, it's existence itself. Space-time. Reality. The universe is literally creating something from nothing. Continuously. At every point in space. Right now. You might think this violates energy conservation. And classically it does. You can't create energy from nothing. But in general relativity, energy conservation is more subtle. Energy is only conserved in static space-times. In expanding space-times, energy can be created or destroyed as space itself changes. Dark energy violates energy conservation. Every cubic meter of new space brings with it the same density of dark energy. As the universe expands, the total amount of dark energy increases. Energy is being created. Where from? The gravitational field. The dynamics of spacetime itself. The fact that expansion does work against gravity. This sounds like a perpetual motion machine. Free energy. Something from nothing. And in a sense it is. The universe is the ultimate perpetual motion machine. Running on borrowed energy from gravity. Creating more space. More vacuum. More dark energy. Forever. Until the Big Rip tears everything apart. Or until vacuum decay resets the universe. Or until we discover that our understanding is completely wrong. But for now, this is what observations tell us. The universe is creating energy, violating classical conservation laws, running on quantum fluctuations and gravitational dynamics we barely understand. And it's been doing this for 13.8 billion years, creating more and more space, more and more energy, more and more quantum foam. An infinite pyramid scheme that somehow works. That hasn't collapsed. That might never collapse. The universe is the greatest scam ever devised. And it's not even conscious. It's just following the laws of physics. Laws that permit this seemingly impossible behavior. Now think about information. In quantum mechanics, information cannot be destroyed. This is a fundamental principle. The unitarity of quantum mechanics. Information can be scrambled, hidden, encoded in complex ways, but not destroyed. Black holes seem to violate this. They swallow information. Anything that falls past the event horizon is gone forever. Classical general relativity says the information is lost. But quantum mechanics says it can't be. This is the black hole information paradox, one of the deepest problems in theoretical physics. Stephen Hawking worked on this for decades. Initially, he argued that information was destroyed, that black holes were exceptions to quantum mechanics. That information paradox was real and quantum mechanics needed modification. But eventually, he conceded he was wrong. Information isn't destroyed. It's encoded in the Hawking radiation, in subtle correlations between emitted photons, hidden in ways we don't fully understand yet. This led to the holographic principle, the idea that all information in a volume of space is encoded on its boundary, that the interior is redundant, that reality is fundamentally two-dimensional, projecting the illusion of three dimensions. But here's the connection to cosmic expansion. What happens to information when regions of space become causally disconnected? When galaxies cross the cosmic horizon? If information cannot be destroyed, but also cannot escape from beyond the horizon, where does it go? Is it encoded on the horizon itself? Like a black hole event horizon, but cosmic scale? Is the boundary of our observable universe a holographic screen containing all the information from beyond? Some cosmologists think so. They've calculated the entropy of the cosmic horizon, the amount of information it can contain, and it's enormous. About 10 to 122 bits. That's the total information content of everything we can observe. And as the universe expands, the horizon grows. More surface area, more capacity for information, more entropy. But what about the regions that cross beyond the horizon? What about the information in those galaxies we can no longer see? If holography is correct, that information transfers to the horizon, gets encoded on the boundary, becomes part of the cosmic hologram. We lose access to it, can't decode it, can't extract it. But it's not destroyed, just hidden, encrypted in patterns we can't observe. This makes the cosmic horizon similar to a black hole horizon. Both are boundaries beyond which information cannot escape. Both encode information holographically. Both have entropy proportional to their surface area. This is called the de Sitter horizon. Our universe, dominated by dark energy, is approaching a de Sitter space-time. A space-time with a cosmological event horizon. A boundary beyond which nothing can be observed or accessed. And if we live in a de Sitter space, then we're living inside something functionally similar to a black hole. Trapped inside a region with a finite information capacity. Unable to access anything beyond our horizon. From an outside perspective, if such a perspective existed, our observable universe would look like a black hole. A region of space-time causally disconnected from the exterior, with information encoded on its boundary. Except there is no outside perspective. We're the entire universe, as far as we can tell. There's nothing outside. No external observer. No higher dimensional bulk for us to be embedded in. Or maybe there is. And we just can't access it. Can't observe it. Can't prove it exists. This is the fundamental limitation of cosmology. We're inside the system we're studying. We can't step outside. Can't see the whole picture. Can't verify our models against some external reality. We're like prisoners in Plato's cave, watching shadows on the wall, inferring the real world from limited observations, building models, making predictions. Sometimes the predictions work. Sometimes they fail. And when they fail, we adjust our models, add new components, dark matter, dark energy, inflation, fine-tuning. But we never know if we're getting closer to truth or just adding epicycles, making our models more complicated without making them more correct. This is the existential crisis of modern cosmology. We have a model, lambda CDM, that matches most observations. But it requires mysterious components we don't understand. Dark matter, dark energy, inflation, fine-tuned initial conditions. And we have anomalies. The Hubble tension, the axis of evil, the cold spot, tensions in the growth rate of cosmic structure, discrepancies in measurements of the matter density. Are these real problems? Or measurement errors? Or statistical flukes? We don't know. And we might never know. Because we only observe one universe. One realization of cosmic history. We can't run controlled experiments. Can't compare our universe to others. Can't verify that our observations are typical or atypical. This is called the cosmic variance problem. We have a sample size of 1. And you can't do statistics with one data point. Maybe our universe is weird, unrepresentative, a statistical outlier, and the theories we build to explain it are overfit, specific to our particular cosmic history, not generalizable. Or maybe our universe is typical, and our theories are correct, and the anomalies will be explained with better data. We won't know until we gather more observations, build better instruments, or somehow access other universes for comparison. That last option seems impossible. But there are proposals. Cosmic archaeology, looking for collision signatures in the CMB, evidence that other bubble universes collided with ours, or looking for asymmetries, patterns that suggest our universe has boundaries, edges, specific topology, connections to other regions. Some cosmologists have searched for these signatures. So far, nothing definitive. But the search continues. Because if we could confirm that other universes exist, even if we can't visit them, it would transform our understanding, give us context, comparison points, a sense of whether our universe is typical or special. And it would answer a deep question: are the laws of physics we observe necessary? Or contingent? Could they be different in other universes? Are the constants of nature fine-tuned by chance? Or by some deeper principle we haven't discovered? This is the multiverse question, the landscape problem, the anthropic principle debate. If other universes exist with different physical constants, then maybe ours is special only because it permits life. Because observers can only exist in universes where the constants allow complexity. Chemistry, biology, consciousness. This is the weak anthropic principle. We observe the universe we do because we couldn't exist in most other possible universes. Selection bias. Observation bias. It's not satisfying. It doesn't explain why the multiverse exists. Why different universes have different constants. Why reality permits such variation. But it might be true. And if it is, then asking, why are the physical constants what they are, is like asking, why was I born in this century rather than another? The answer is, if you weren't, you wouldn't be asking. Not satisfying, but possibly correct. The alternative is that the constants are unique, determined by some deeper theory we haven't discovered. A theory of everything. A final equation that predicts every constant, every parameter, every feature of reality. This is the dream of theoretical physics, the Holy Grail. Einstein spent the last decades of his life searching for it. Failed. Died without finding it. String theory promised to be that theory. A unified framework explaining all forces, all particles, all interactions, deriving the constants from first principles. But string theory has a problem. It doesn't predict one unique universe. It predicts 10 to 500 possible universes. A vast landscape of solutions, each with different constants, different physics. And we have no way to calculate which solution corresponds to our universe. No way to navigate the landscape. No way to predict anything. String theory went from theory of everything to theory of anything. From explaining everything to explaining nothing. Some physicists abandoned it. Moved to other approaches. Loop quantum gravity. causal sets, asymptotic safety, emergent gravity. Others doubled down, argued that the landscape is a feature, not a bug, that our universe is one solution among many, that we observe it because we can only exist in universes with our particular constants. Anthropic reasoning, multiverse, landscape. Not satisfying, but maybe true. The debate rages. Conferences, papers, arguments. No resolution in sight. Because without observational evidence, theoretical physics becomes philosophy. Untestable speculation. Beautiful mathematics with no connection to reality. And that's dangerous. Physics has always been grounded in experiment, in observation, in testable predictions. When physicists stop making testable predictions, they stop doing physics. They start doing mathematics, or philosophy, or theology. Not that those are bad, but they're different. They operate under different rules, different standards of truth. Physics requires experimental verification. Without it, physics dies, becomes untethered from reality, drifts into abstraction. This is the crisis facing fundamental physics today. We've built theories, string theory, multiverse, inflation, that make few or no testable predictions. That might be correct but might be unfalsifiable. And unfalsifiable theories aren't science. They're metaphysics. So where does that leave us? We know the universe is expanding. We've measured it, confirmed it, understood the basic mechanism. General relativity plus dark energy plus initial conditions. But the deeper questions, what is space expanding into? Why does dark energy exist? What happened before the Big Bang? Those might be unanswerable. Not because we're not smart enough, but because they're outside the domain of empirical science. If a question has no observable consequences, no testable predictions, no way to gather evidence, then it's not a scientific question. It's philosophical. And maybe that's okay. Maybe some questions are philosophical. Maybe the boundary between physics and philosophy is fuzzy. Maybe we need both to make sense of reality. But we need to be honest about it. When we're doing physics and when we're doing philosophy. When we're making testable claims and when we're speculating beyond evidence. The universe is expanding. That's physics. Well tested. Confirmed. The universe is expanding into nothing because space doesn't require a container. That's philosophy. Untestable. Possibly meaningless. Both might be true. But they're different kinds of truth. Different epistemic categories. And conflating them leads to confusion. To overselling speculation as fact. To presenting untested theories as established science. We need to be careful. Precise. Honest about what we know and what we're guessing. Because the universe doesn't care about our theories. It is what it is. Whether we understand it or not. Whether our equations describe it or not. And our job, as conscious beings, as seekers of truth, is to observe carefully. Theorize humbly. Test rigorously. And accept the results, whatever they are. Even if the results are incomplete. Even if they leave questions unanswered. Even if they reveal that some questions can't be answered. That's the nature of reality. Complicated. Messy. Partially knowable. Partially mysterious. The universe is expanding into nothing. Or into something we can't observe. Or the question doesn't make sense. We've made progress. Gathered data. Built models. Explained a lot. But mysteries remain. And maybe always will. Because we're finite beings trying to comprehend infinity. Local observers trying to understand the global structure. Parts trying to grasp the whole. It's an impossible task. And yet we attempt it anyway. Because we're human. Because we're curious. Because we can't help ourselves. The universe is expanding. Taking us with it. Creating more space. More distance. More separation. And we're here. Observing. Measuring. Calculating. Trying to make sense of the senseless. Trying to comprehend the incomprehensible. That's our gift. and our curse. Consciousness in an expanding universe. Awareness in a cosmos that doesn't care. Intelligence confronting mystery. We'll never have all the answers. But we'll never stop asking the questions. That's what makes us human. What makes us matter. What gives meaning to our brief existence in this vast, expanding, indifferent cosmos. We are the universe asking what it's expanding into. And the fact that we can ask, even if we can't fully answer, is itself extraordinary. Improbable. Precious. You are that question. That curiosity. That drive to understand. And that's enough. That's everything. That's why you're here. The expansion rate isn't uniform across cosmic time. It changed. Dramatically. Multiple times throughout the universe's history. In the first fraction of a second, during inflation, space expanded exponentially, doubling in size every 10 to 37 seconds. In less than a blink, a region smaller than an atom became larger than the observable universe today. This is insane. Impossible. Yet it happened. Then inflation ended. The expansion rate dropped catastrophically. From exponential to polynomial. From unimaginably fast to merely very fast. For the next several billion years, the expansion decelerated. Gravity was winning, pulling everything back together, slowing the cosmic dispersion. Scientists in the 1990s expected this deceleration to continue forever. They were measuring how much the expansion had slowed, trying to determine if the universe would eventually recollapse, the Big Crunch, or expand forever but ever more slowly. Then they measured distant supernovae, Type I supernovae, standard candles, objects with known intrinsic brightness. By measuring how bright they appear, you can calculate their distance. And what they found broke cosmology. The distant supernovae were dimmer than expected, farther away than they should be, which meant the universe wasn't just expanding, it was accelerating, speeding up. This made no sense. Gravity should slow expansion, not accelerate it. Nothing in known physics could explain this. Unless there was something else. Something with negative pressure. Something that pushed rather than pulled. Something that made up most of the universe but was completely invisible. Dark energy. The 1998 discovery of cosmic acceleration won the Nobel Prize in 2011. And it introduced the biggest mystery in physics. What is dark energy? Where does it come from? Why does it have exactly the density it has? The simplest explanation is the cosmological constant, lambda, a term Einstein added to his equations to make the universe static, then removed when Hubble discovered expansion. Called it his biggest blunder. Except it wasn't a blunder. Lambda was real, just smaller than Einstein thought, and positive, causing acceleration rather than static balance. The cosmological constant represents the energy of empty space itself. The quantum vacuum. Every cubic meter of space has the same energy density, about 10 to minus 9 joules per cubic meter. That doesn't sound like much. But multiplied by the volume of the observable universe, about 4 times 10 to 80 cubic meters, and you get 10 to 71 joules. More energy than all the matter in the universe combined. And here's the kicker. Quantum field theory predicts the vacuum energy should be 10 to 120 times larger than what we observe. That's not a typo. 120 orders of magnitude too large. This is called the cosmological constant problem. The worst prediction in the history of physics. Off by a factor with 120 zeros. If the vacuum energy were as large as quantum field theory predicts, the universe would have blown apart instantly. No atoms. No stars. No galaxies. No you. So why is it so much smaller? Why is it precisely the value that allows structure to form? Galaxies to evolve? Life to emerge? We don't know. Maybe there's a mechanism that cancels most of the vacuum energy, leaving only a tiny residual. But we haven't found that mechanism. Don't even know what it might look like. Or maybe anthropic selection. Maybe most universes have different vacuum energies. And we observe the value we do because it's one of the rare values compatible with observers. Again, not satisfying, but possibly true. The cosmological constant might not be constant. It might be dynamic. A field that changes over time. Quintessence. Phantom energy. Rolling scalar field. If dark energy is dynamic, then the expansion rate might change again. Might accelerate faster, or decelerate, or oscillate. We're measuring this precisely using supernovae, baryon acoustic oscillations, gravitational lensing, multiple independent methods. So far, all measurements are consistent with a constant lambda. No evidence for evolution, no variation. But our measurements only span the last few billion years. A tiny fraction of cosmic history. Dark energy might vary on longer timescales. Might have been different in the early universe. Might change in the future. If it does, our predictions about the universe's fate are wrong. The Big Rip might not happen. Or might happen sooner. Or something else entirely might occur. We're flying blind into the cosmic future. Extrapolating from limited data. Hoping our models are correct. Knowing they might not be. Think about the implications of accelerating expansion for causality. For the fundamental structure of cause and effect. In special relativity, causality has a speed limit. Light speed. Cause and effect propagate at maximum 299,792 km per second. Events outside your light cone cannot affect you. Cannot be affected by you. This creates a causal structure. A network of what can influence what. Past light cone, events that could have caused your current state. Future light cone, events you could potentially cause. Everything outside both cones is causally disconnected. Happening simultaneously in your reference frame, but unable to interact with you. But in expanding space, this gets complicated. Light cones don't extend to infinity. They're truncated by the cosmic horizon. Beyond a certain distance, events can never affect you. Not now. Not ever. Your future light cone has a finite extent. You can only influence a finite region of space. Galaxies beyond that region will never receive any signal from you. Will never know you existed. This creates cosmic loneliness. Fundamental isolation. Not just practical. We can't build spaceships fast enough, but theoretical. The laws of physics themselves prevent communication beyond a certain distance. And that distance is shrinking. As dark energy accelerates expansion, more and more galaxies slip beyond the horizon. Your future light cone shrinks. Your ability to influence the universe diminishes. Eventually, you can only affect your local galaxy group. Then only your galaxy. Then only your stellar neighborhood. Then only your solar system. The sphere of possible influence collapses. Until you're effectively isolated. Trapped in a tiny bubble of causally connected space. Surrounded by infinite, unreachable universe. This is the heat death from a causal perspective. Not just thermodynamic equilibrium, but causal disconnection. The universe fragmenting into isolated pockets that cannot communicate. Cannot interact. Cannot even know about each other. Each pocket might as well be its own universe. Its own reality. Completely separate from all the others. The multiverse doesn't require parallel dimensions. Just patience. Just waiting for expansion to isolate us. To create natural boundaries between causally disconnected regions. We're already in a multiverse. We just don't realize it yet. Because the boundaries are still beyond our horizon. Still outside our observational limits. But they're closing in. Every second. Irreversibly. The cosmic event horizon is currently about 16 billion light-years away. Galaxies beyond that distance are receding faster than light. We can still see them. Their light was emitted when they were closer, but we can never reach them. Never send signals to them. Never affect them in any way. And galaxies just inside that horizon? They're slipping across. Every day. Thousands of them. Crossing the boundary. Vanishing from our future. Forever. Imagine watching a galaxy approach the horizon. You can still see it, still observe its light, still study its stars and gas and black holes. But you know, with absolute certainty, that anything happening in that galaxy right now will never be observable, never reach you. The light being emitted at this instant will never cross the expanding space between you. That galaxy is dying to you, not physically, but informationally. It's becoming past tense, history, fixed, no longer part of your future, only your past. And eventually, billions of years from now, even the old light will fade, redshifted beyond detection, until the galaxy disappears completely. From sight, from knowledge, from possibility. Where did it go? Nowhere. It's still there, still existing, still evolving, still full of stars and possibly life and civilizations. But for you, it's gone, erased, as if it never existed. This is the true cost of expansion, not just spatial separation, but informational death. The gradual erasure of cosmic history, the forgetting. The universe has Alzheimer's. It's losing its memories, its connections, its coherence, breaking apart into isolated fragments that don't remember each other, can't communicate, can't verify each other's existence. And we're one of those fragments, slowly losing contact with the rest, watching the universe fade, disconnect, vanish. You think death is scary? Individual death? The cessation of one consciousness? Try cosmic death. The death of causality itself. The fragmentation of reality into isolated, unreachable pieces. The heat death isn't just cold. It's lonely. Profoundly, utterly, irreversibly lonely. Every intelligent civilization in the universe will eventually face this. Watch their neighbors disappear, one by one, galaxy by galaxy, until they're alone. And they'll build telescopes, gather data, preserve observations, create archives of the universe as it once was, when it was connected, observable, knowable. Those archives will be precious, irreplaceable, the only remaining evidence that the universe was once larger, once filled with more galaxies than they can currently see. Future civilizations might doubt those archives, might think they're myths, fairy tales, because their observations show only local structure, no distant galaxies, no CMB, no evidence of expansion. They'll develop theories based on what they can see, and those theories will be wrong, incomplete, missing the bigger picture, unless they trust the archives, the ancient data, the observations from a time when the universe was still young and connected. Will they? Or will they dismiss it as superstition? Primitive misunderstanding? Ancient astronomers who didn't know better? We can't know. But it's a sobering thought. That everything we're learning now, all our cosmological knowledge, might be lost, forgotten, disbelieved by future generations who can't verify it. This is why we observe, why we measure, why we archive, not just for ourselves, but for the future, for those who come after, who will need this knowledge, this evidence, this proof that the universe was once greater than what they can observe. We're creating cosmic memory, recording the universe while it still remembers itself. Before the expansion erases everything, before the isolation becomes complete. This is the sacred duty of cosmology. Not just understanding, but remembering, preserving, witnessing. The universe is expanding into nothing, and in doing so, it's erasing itself, disconnecting, fragmenting, dying by degrees. And we're here, right now, at this unique moment, when we can still see, still measure, still know. This moment won't last. The universe is giving us a gift, a window of observability, a chance to understand our cosmic origins before the evidence vanishes. We must use it wisely, observe carefully, record faithfully, because this opportunity won't come again. The expansion continues. The horizon shrinks. The isolation deepens. And someday, far in the future, our descendants will look at our observations and wonder if we were right. If the universe really was that large, that old, that magnificent, they won't be able to verify it. The evidence will be gone, redshifted beyond detection, separated beyond observation. They'll have to trust us. Trust that we observed carefully, calculated correctly, recorded faithfully. That's our legacy. Not monuments, not art, not even technology, but knowledge. Cosmic knowledge. The truth about reality before expansion hid it forever. We are the universe's witnesses, its memory keepers, its historians. And what we observe now, this expanding cosmos, accelerating into isolation, is the story we must preserve. For ourselves. For the future. For truth itself. The universe is expanding into nothing, creating isolation, erasing connections, fragmenting reality. And we're documenting it, understanding it, accepting it. That's our role, our purpose, our contribution to cosmic history. We saw, we measured, we understood, we remembered. And that memory, recorded in data, in papers, in archives, will outlast us. Will outlast our civilization. Will persist as long as information itself persists. The universe is forgetting, but we're helping it remember. Creating external memory. Artificial persistence. Knowledge that survives the expansion. That's not nothing. That's everything. That's the whole point of consciousness in an expanding universe. To observe. To understand. To remember. To preserve. The universe is expanding into nothing. But we're expanding into knowledge. Into understanding. Into cosmic significance. And that expansion, of mind, of awareness, of comprehension, is the only expansion that truly matters.